Vale, sí, perfecto. Muchas gracias. Yeah, it's like a matter of weeks. Okay. Okay. Perfect. Thank you very much, Patricio, for the nice introduction. And thank you all for coming. I'm delighted to be here sharing my work. And if you prefer to interrupt me to ask questions during the talk, feel free to do it. I'm going to talk, as Patricio said, as the work that I've been doing during the last couple of years on axion-like particles, especially around the multi-electronvolt mass range. And this is work that I've done with Andrea, Gabriela Satopolito, Marka Mionkowski, and Jordan Miroka. Oh, that archive number is only for one of the papers. I forgot to update that, sorry. But you'll see it on the around like the slides that appear. Also, since I know that there may be some people working more on the part of particle physics on dark matter, I want to stress that I work on this side from the phenomenological side, so I'm not going to talk so much about model building and so on. So just as introduction, I want to give a brief snapshot of where is cosmology right now. As you all know, we are well in the era of precision cosmology, thanks especially for the work both in experimental theory of the main cosmological observables that are the cosmic microwave background, galaxy clustering, and the studies of the baryon acoustic oscillations, gravitational lensing, supernovae, and also very recently gravitational waves. And this has established the standard cosmological model, which is lambda cold dark matter, which is a very successful model. It reproduces with astonishing precision most of the observations, but it has some flaws, both on the experimental and the theoretical side. On the experimental side, I have worked on some of these, but I'm not going to talk about it today. There are persistent discrepancies between different cosmological probes with some curious trend that it may be that these tensions are between probes of the early and the late universe. I'm sure that you're aware of like the tension in the Hubble constant. Now the tension on the clustering, which is parameterized with this parameter combination, is starting to get more and more significance. And I have worked especially on the one of the Hubble constant. So if you want to talk about it later, feel free to come and ask me. I'm going to be here for a couple of days. But I'm going to talk more about the fact that lambda CDM is a phenomenological model that doesn't attempt to provide a microscopic explanation for what is the nature of dark energy, dark matter, or what was the physics in the primordial universe. Especially, I'm going to talk about one of them, the one of the dark matter. So I think that there are three main ways to tackle these challenges that the model of lambda cold dark matter and the current situation in cosmology stays. That is, first, the improvement of the current set of observations, improving sensitivities, improving the analysis of the data, but also, and this is the one that I'm most interested in, the exploration of new cosmological probes to basically not only access new information and independent ones, but also access new regimes that can't be explored with current cosmological probes. And also, and this is the one that I'm less familiar with, the exploration of new models that could be alternatives to lambda cold dark matter. And the motivation of most of my talk, and I'm going to talk today about it, is the recent measurement of around 4 sigma excess in the cosmic optical background, and a potential explanation of the dark matter, and therefore the motivation for exploring axion-like particles in the mass range that I'm going to talk about. So, in order to introduce the measurement of the cosmic optical background, let me start with talking about the extragalactic background light. The extragalactic background light is basically the whole integrated flux of all emitted radiation in the universe. So, therefore, it can provide us with a census of all emitters. And this is very good because it also captures the intensity and the emission from first sources that we can't resolve with, for example, galaxy arrays. The problem of this is that especially around the optical and the infrared ranges, this is very hard to measure because of the contamination of the zodiacal light, which is the sunlight scatter of planetary dust. And that's why all these direct measurements here are in the end so all over the place with huge error bars and very marginal, maybe to sigma detection. But there is also a current effort with archival data of Hubble, which is called SkySurf, in order to reassess the levels of the zodiacal light. And they are seeing that basically there is no, from the Hubble Space Telescope, there is no detection of the extragalactic background light. Thankfully, there are other approaches to measure this in a more indirect way or to estimate it from theory. And the one that I'm going to talk more today is the one from the attenuation of gamma rays. But also we can infer it from the galaxy counts and extrapolating the luminosity functions and perform also some theoretical estimates. Recently, as I was saying, there was the first very high significant detection of this cosmic optical background by the LORRI camera in the New Horizons spacecraft. And this was possible because this spacecraft is basically right now beyond the solar system, beyond 50 astronomical units from the sun. And the LORRI camera is basically a white filter between 0.1 and 0.9 microns with a pivotal wavelength at 0.61. And as I said, this is the first high significant detection. And surprisingly, with respect to the expectations from both galaxy number counts in deep fields of Hubble and the attenuation from gamma rays, which would be these lines and bands for the 1 sigma, you can see that this is basically twice what would be expected in this wavelength range. And this significance for this excess is 4 sigma. So it's something serious. It's not something that it can be like a fluctuance. And the work of the New Horizons team and the LORRI camera team made magnificent work on trying to find potential contamination for this measurement. There are several potential explanations for this contribution, for like astrophysical contributions, and I'm going to start from the less exotic to the more exotic. It could be that the extrapolation of the galaxy luminosity functions for the faint end, it's wrong, and there are many more faint objects that we expect, as was theorized by Conselizzi and collaborators in 2016, but this would be very hard to achieve with the current models of galaxy formation. It could be also intrahalo light, that is basically the radiation from stars that have been tidally stripped from galaxies, and now they live in the halo, but with a surface brightness that is too faint to be detected in the individually and to be resolved. And but I mean, this would be that the contributions from intrahalo light should be twice the contribution from the galaxy that we know. So this, it seems that is a lot to be accounted for intrahalo light. And finally, there could be also contributions from the very high redshift and bright objects, such as, for example, could be the theorized direct collapse black holes, which is a nice candidate for the population of very high mass and high redshift supermassive black holes that we have observed, but still there's no evidence of them. And again, this will be a pretty high contribution. So basically, when I saw this, I thought, what if this is the contribution from dark matter decays, axion-like particles that, in order to generate these photons from these energies, they have to be in the multi-electronvolt. So let me step back and introduce a bit the axion as a candidate of dark matter, and later I'm going to come back to the measurement of the cosmic optical background. So the axion is a pseudo-Nambu-Goldstone boson that was initially proposed to solve the SCP problem, but it was naturally also a potential dark matter candidate. It has, among other things, a coupling with photons that generates the famous oscillations with the photon and the axion in the presence of magnetic fields. But the one that I'm going to be focusing more is that it triggers a radiative decay, which basically would be an axion decaying into two photons, which have a monochromatic energy, and therefore this would be an emission line from dark matter decays, which is going to be very important also for some of the parts that I'm going to talk later today. And the decay rate for this for this process is basically related with the mass of the axion and the effective coupling between the axion and the photon. So I'm going to be talking indistinctively between the coupling and the decay rate. Okay, perfect. The axion-like particles are also very famous and very relevant in searches in the ultralight mass regime, which are also known as wave dark matter or fuzzy dark matter. This is very interesting because there are some effective self-interaction due to the quantum processes that suppresses the clustering at small scales, but I'm not going to focus about it today. And I'm going to be talking also indistinctly between axion and axion-like particles because beyond the coupling required to solve the QCD problem, not the QCD axion, these are not the same that were proposed to solve it. So this is right now the current status of experimental searches and forecasts and future experimental searches for the axion. As you can see, this is not even including the ultralight axion, and this spans almost 20 orders of magnitudes in mass. But here, all of these are 95% confidence level constraints or forecasted sensitivities. The sensitivities are the ones that are half transparent. But in order to explain the cosmic optical background, we need to be in this range here that, as you can see, it seems to be the hardest to probe because you have this strength here for lower masses, you have these that have been already observed, and here we only have the constraint from the stellar cooling and the measurements in globular clusters and the searches of with optical telescopes in galaxy clusters. So now that we are there, basically what we did before in order to start thinking about this is whether the decay of the axion could explain this or could contribute for this excess. So what we did was predict the contribution for the intensity on the optical background of the axion in the wavelength that would be measured by Lorry and the responsivity of the Lorry camera, which is, of course, proportional to the decay rate. And this set star is basically the action of the recipe of the decay of the axion that depends on the mass of the axion. And surprisingly and very excitingly, here would be the region of the parameter space of the axion that could explain the excess in the cosmic optical background at 95% confidence level. As you can see, here we have the constraints from the telescopes, the optical telescopes, and the stellar cooling that I mentioned before. So above 8 electron volts, we would be in a region of the parameter space that hasn't been ruled out. So this was very exciting. This means that the axion-like particles could contribute to explain the excess. And we found that it was also overlapping with the 1 sigma preferred region from a study of the gamma ray extinction from Korochkin and collaborators that studied a single blazar. So this motivates us also to go further in the study of the gamma ray attenuation and perform a much more systematically study that I'm going to talk about now to see whether this overlap was a hint that it was actually the axion contributing to this. And what is also very exciting is that in the future, limb surveys, and this is a work that I did last year, will be able to probe this region of the parameter space with a lot of sensitivity. And if I have time, I will also talk about this forecast. For you to have some kind of intuition right now, these lines here corresponds to the forecast from the power spectrum of line intensity mappings and the voxel intensity distribution, which is basically the one-point statistics of the intensity maps, as observed by spherics that will be launched in a couple of years, and hetex that is already observing. So this is a very exciting situation. But first, let me talk about the studies that we can do with gamma ray attenuation in order to probe the extragalactic background light and therefore the contributions from the axions. Basically, the flux of very high energy gamma rays from distant blazars gets attenuated by photons in the EBL, in the low range energy between the infrared and the near ultraviolet, due to the annihilation of photons into pair production of positron and electron. This process, of course, has a minimum energy threshold to do it. That is basically the mass of the two electrons in the rest frame, and the the cross section for this process peaks around the minimum energy. So basically, it's not a one-to-one relation, but if we know the energy of the gamma ray at a given redshift, we kind of know the range of energies of the EBL photons that it's going to be interacting with. And I took this, this diagram for the recent review of Vito and Meyer to how to probe fundamental physics with gamma ray attenuation. And this basically is what's going on. So we have the blazar in a distant galaxy, emits the photon, and it should arrive if nothing happens to us in the Milky Way. But as it interacts with EBL photons, it's going to produce electrons that are going to be in the presence of intergalactic magnetic fields, are going to be deflected. And if there is a secondary production of gamma rays, for example, with an interaction of a CMB photon, basically by the point spread function of the blazar in gamma ray observatories, we can probe the intergalactic magnetic fields. We can also probe the axion in the nano-electron-volt regime, because with the magnetic field of the host galaxy of the blazar, there might be an oscillation from the gamma ray to be an axion, and therefore the axion doesn't see at all the EBL photons, and with the magnetic field of the Milky Way, could transform back into an axion, and into a photon, into a gamma ray that will be detected. So basically, this could be similar to a light-through wall experiment in Earth, but in this case, the wall would be the EBL photons. And therefore, in this case, we would be expecting to see an excess of gamma rays with respect to what we would be expecting from models of the EBL. However, I'm going to be focusing only on the annihilation of the EBL in order to quantify the extragalactic background light. So I'm going to do this basically from the measurements of the optical depth from around 800 blazars from the Fermilab collaboration and another Cherenkov telescopes. So here you already see a very big difference with the work of Korochkin et al., because they were using only a single blazar, and we are using 2 orders of magnitude or almost 3 more blazars. And basically what we are going to be targeting is the optical depth of those blazars. Now, this is much more, it has much more information than of the optical background, because in this case we have tomographic and chromatic information, because the optical depth is the line of sight integral of the inverse of the mean-free path, which is basically the product of the cross-section and the number density of low energy photons. And therefore, since it's the line of sight integral, the farther is the we have information around by having several blazars at different distance. So in this case, we have a tomographic information of the EBL, and also since the cross-section depends on the energy of the gamma ray and the energy of the low energy photons, we also have a chromatic information of the EBL that with the Lorry camera, since we had a white filter, we did not have. And there are like many science cases that we can do with gamma ray attenuation. First of all, we can probe the EBL. And if we assume some contributions from the EBL, on top of the axion-photon oscillations that I mentioned, there have been studies of probing the expansion rate of the universe, basically constraining here the Hubble rate. The error bars for this are still pretty high to be competitive with other probes of the spatial history of the universe. And there can be constraints for different contributions to the EBL. There have been studies for population 3 stars. And also the axion decays was basically proposed in a couple of papers by Kalashev and collaborators in 2018 and preliminary attempted by Koroskin and collaborators. So basically, the way this optical depth is measured is, since we don't know the intrinsic spectrum of the blazars, they have been binned in intervals of the observed energy of the gamma ray and the source redshift of the blazar. And since the optical depth must be the same for all of them, because the mean free path is too large in order to be caring about the fluctuations in the large scale structure, basically, we can marginalize over the intrinsic spectrum, and with a common optical depth, we get a very good measurement of the optical depth. And basically, once we have these measurements, we need to estimate or quantify the standard contributions to the extragalactic background light. And we distinguish 3 different contributions. First, we consider galaxies at below redshift 6, and we take this from Saldania, Lopez, and collaborators last year, which is an observational determination from observations of the Hubble and the Candle surveys of deep fields from galaxy number counts. And this is by far the most dominant contribution, as expected, to the EBL. We also consider the contributions of galaxies before reionization beyond redshift 6. And we did this with a theoretical determination using the code ARES, that with a model that has been calibrated with luminosity functions in the ultraviolet and also accounted for the contributions of population 3 stars. And finally, for the intrahalo light, we use a theoretical model that has been calibrated to the near infrared and optical background fluctuations. In all of them, we also account for uncertainties, and in the 2 theoretical cases, we take extreme cases for the minimum and the maximum of those contributions in order to be more conservative. So we compute the optical depth that is associated to each of these contributions, and basically remove it from the measured optical depth in order to try to obtain a residual optical depth that can't be accounted for any of these contributions. And we assume that the errors for these contributions are independent. We set them in quadrature. And the first step of our analysis is whether there is or not a residual optical depth consistent with 0. If there's consistent with 0, basically the thing that we need to do is quantify what limits set that on the contributions from the actions. If it's not, maybe it can be a detection of actions. As expected, because there have been previous studies of comparison with the extragalactic background light from this kind of contributions and the one inferring directly from the gamma ray attenuation, there is a slight optical depth that is above 0. But in order to just like go directly and assume that this is from actions, we also consider 2 null cases. On top of exploring the action parameter space, we first consider an unphysical case, but as a null case, it worked for us, that basically would be scaling the contribution of low redshift galaxies by a constructor in all redshifts and frequencies, and basically fit for this factor F EBL. And as a considering that it could be underestimation of the errors from these contributions, we also boost their errors and increase the uncertainties until we obtain a optical depth residual that is consistent with 0. And in that case, we fit later for an ultra-conservative upper limit in the action parameters. So basically, these are the main results that we get. We have a best fit for the action parameters around the 10 electron volts and for 2.5 times 10 to the minus 24 inverse seconds. And in the case of the scaling up the extragalactic background light from galaxies, we find that we can explain that optical depth with 20% more contributions from these galaxies, plus minus 8%. Now, if we compare the significance over the null hypothesis, which would be no additional contributions to the EBL, we have that the contributions, the additional contributions from galaxies it's preferred slightly by 2.7 sigma over 2.1 sigma. And this is basically because if we compare the two models, there is a 0.7 delta chi squared. Now, this is much higher in sigma because this is only one parameter and this is two parameters. So the chi squared statistics work differently for both. But let's study the delta chi squared as for each beam in the energy of the gamma rays and in the source redshift of the blazars. Because in this case, basically, it will tell us what kind of features in the data prefers one or two or the other model. And as the high redshift blazars basically don't tell us anything. Sorry, I don't know why there's no redshift here. These are like different redshift beams for the for the blazars, and basically for the high redshift there is no preference for any of the models. But at low redshifts we have the very local blazar. This is like 0.03 in redshift, and this is 0.14, I think. And now there's going to be the labels of it. We see that they favor a lot the low redshift, the contributions from galaxies rather than the contributions from axions, while slightly higher redshifts prefer the contribution from axions. So let's look at the data and try to see these patterns here. Again, no labels, sorry. Yeah, that's like, I thought, I read these figures yesterday and I didn't notice that there were no labels. Sorry for that. So if I'm not wrong, this is 0.03, this is 0.14, and this is starting to 0.25 or something redshift. And this is 0.6, maybe? I don't remember. Yeah, it's quite low redshift, but these are like super local ones. So here I saw the data in black. I'm showing the actual measurements from the gamma ray observatories. And in colors, I saw the residual optical depth as I reduce the contributions one by one. You should look at the one that is like the blue or green. I don't know exactly how it looks with the projector contribution, which is the one that have been removed all the considered astrophysical contributions, and we fit to that and so here the best fit for the axions in the black dotted lines, and in the red dotted lines is the best fit for the additional astrophysical contributions. And as you can see, for these two redshift beams, as I was saying, they follow much better the error bars, the measurements, but for higher redshifts, they can't get this, and the contributions from the axion decays is a much better fit. Now, this is a log-log plot with lots of upper limits, so that's why I had this kind of plot, because in this case, checking what is the difference between the measurement and the prediction is very hard. So now we have these results. Let's see first what is the preferred. Sure. So it's a cumulative removal of optical depth. So basically, this shows that the dominant contribution is by far the from galaxies below redshift 6, and basically the removal or the contribution from the other sources is so marginal that basically the three of them look the same. Why is not showing the whole? I think that there are some problems with how they are showing the figures, because in this figure there should be some contours here, and this should be the same for the. So I set the PDF maybe instead of the PowerPoint, because these figures are not so completely. I'm going to try to do that. Sorry for this. Let me see. ver si está. Yeah. Okay. So how do I set the? Oh, okay. Okay, I'm going to set here. Oh. Okay. Yeah, sorry for this, but at least you can see here that the labels were in the figure. Oh, I remember quite well what was the source. Wow, that's impressive. Come on, give me some space here. So yeah, these are basically much higher. What is the? This is much higher energies for the gamma rays because these are the ones observed by Cherenkov telescope. Okay. And is this one, right? Okay. Okay, perfect. And if I do this, no, and I'm going to be okay. I'm going to stay here and move it with this. So these are the contributions from, like, these are the ones observed by a ground Cherenkov telescope. This is why they are much lower rays but much higher energies. And these are the ones already by Fermilab, all these. So they stay at like this is the tera-electron-volt. And at higher redshift, they observe at lower and lower energies because the higher energy gamma rays have been totally attenuated. Let's see. Okay, this was the same plot that as I was showing. Okay, perfect. And this is the contour plot that I was showing. And I'm going to remove this from here. Perfect. And here is a plot that is very similar to the one that I was showing before, but I have enlarged the range in masses. Actually, this is the region that could explain at 2 sigma the optical depth from, the cosmic optical background. These are lines from the 2 sigma upper limits from other surveys or experiments. This is the band that would explain the QCD action. And these are the forecasts from line intensity mapping surveys. But the interesting part here is the contribution from this work, from this analysis. And the good thing is that the best fit that we observe has been unconstrained. It's around here. It's slightly higher than 10 to the minus 24 inverse seconds for almost 10 electron volts. We find at 2.1 sigma, as I was saying before, significance for this measurement. But there are some things in this contour that are not nice, right? First of all, we see this bimodal distribution, which could just be due for this feature that I mentioned before, that there was a bad fit for the local blazars, but a very good fit, but a good fit for far higher blazars. And the fact that the FEBL, the contributions from additional sources from galaxies basically had a better fit than the one of the Axions, made us be skeptical of it and explore other null cases. But what I want you to take from this plot is not the 1 and 2 sigma confidence level contours, but the very strong 3 sigma limit that basically improves in the coupling of the axion and the photon over 1 order of magnitude here with respect to the cooling of stars and the observations of low-large clusters. In trying to understand better what is what part of the data set is driving these results and whether this is real or is just some results from a bad fit, we removed the first beam from the analysis. And in this case, we have a much better significance, a much higher significance over the null hypothesis for the axion, and much stronger preference of the axion of a case of additional contributions from galaxies. But however, the preferred region lies in a region of the parameter space that have been ruled out by observations of galaxy clusters with optical telescopes. So basically, either we have a mixed contribution between an underestimation of the contribution from galaxies at low redshift and actions, or this seems that the result that we were seeing was a poor fit, and we need to be left with the 3 sigma limit that still, for me, is a very strong result. Now, in case, yep. Oh, okay. So if we go back here, basically the mass of the action is going to tell us where this, how they contribute to the EBL, because we are assuming that this is a emission line. Depending on the mass of the action, is going to have a different energy for the EBL photons. So that's going to be attenuating a set of gamma rays at a given redshift. So it's somewhat integrated, so it's hard to tell which exactly it is. But in this case, we have that tomographic and chromatic information. Okay, so this could be kind of like the first null case that we were exploring. For the second one, as I remember you, this was basically boosting the errors until we have no residual optical depth, or that one is consistent with 0. This is the 3 sigma constraint that we have in that case. And we are still, in this ultra-conservative case, we have the strongest limits between 8 and 25 electron volts, totally improving the contribution, like the current constraints from global clusters. Now, this line here is from the old paper from Ajala and collaborators. I just noticed today that there's a very recent paper only a few weeks ago that improves this constraint a bit better, not using only the horizontal branch, but also the asymptotic giant branch in the evolution of the stars in the globular clusters. But that only improves slightly this line. So instead of being here, it would be around here. So we still have by far the strongest limits on the optical depth. And also note that this is 3 sigma, not 2 sigma. So comparing it 1-to-1, ours would be even a bit lower. So how much time do I have? 15 minutes. Okay. So if there is no further questions about this part of the talk, I'm going to talk briefly about this forecast from line intensity mapping. I've been working a lot in line intensity mapping for the last years. And one of the cases that we studied was basically the contributions from exotic decays and how this could be forecasted. But let me start first about talking what is line intensity mapping. Line intensity mapping is a technique that uses the integrated signal without recurring any detection threshold or without trying to resolve any source. And in this sense, it's very similar to what I was saying before about the cosmic optical background. But in this case, we have very good spectral resolution. And also, instead of getting all the contributions, identifiable emission lines are targeted in order to resolve the radial coordinates and build three-dimensional maps, because if we know which line we are targeting and we have a good spectral resolution, we know the redshift that this emission is coming from. And in that case, we can not only probe the astrophysical processes that trigger the emission of these lines and basically probe the interstellar intergalactic medium, we also can probe, if we have a big enough footprints in the sky, the large scale structure. And in this case, this would be very similar to large scale galaxy surveys. But since we don't require any detection threshold, we can reach much higher in redshift to the point where galaxies are too sparse and too faint in order to be resolved. So this example from Patrick Brise is within a simulated field, comparing the detections from, this could be the galaxies, 4,500 hours of BLA, and this would be the red dots, the only galaxies that could be detected. In a galaxy survey, this could be just basically number counts. If we compare this with a line intensity map with a third of the time with COMAP, we will see these results. Now, the resolution is much worse, but we can get fluctuations in the large scale structure in here that could be avoided in this observation. So basically, in summary, galaxy surveys give you a detailed distribution of the brightest galaxies, while intensity maps give you a noisy distribution of all the galaxies and the AGN, and still tracing the matter density of the universe, and therefore probing the large-scale structure, as I said before. In order to use intensity mapping for cosmology, we can use the power spectrum, as is customary in cosmology, but the problem is that the intensity maps are very highly non-Gaussian, and this is because on top of all the non-Gaussianity from the gravitational collapse and non-linearity of galaxies, we have all the complexity from the emission and intensity of these lines. So there is still non-Gaussianity, and therefore lots of information beyond the power spectrum. Furthermore, in the simplest formulation of the power spectrum, the matter power spectrum only depends on the first and second moment of the luminosity function, therefore leaving a lot of astrophysical information out. So we get good information about cosmology from the power spectrum, but not about astrophysics. In order to get that information, we can use the one-point statistic that I mentioned before, the Boxer intensity distribution, that encodes the full luminosity function. And as any one-point distribution is basically an estimator for the PDF of the intensities that we can observe in a Boxer. So again, as a rule of thumb, power spectrum is good for cosmology because it depends on integrals of the luminosity function, while the BID is best for astrophysics and only depends on integrals of the clustering. Right now, we can also combine these two statistics because thanks to some work that I've done with Gabriela Satopolito on deriving the covariance for the two summary statistics of the maps. So how are we, sorry, intensity maps have some drawbacks though. They are more sensitive to contamination than galaxy surveys. And I'm sure that you all are very familiar with the H1 surveys, 21 centimeters, and there the main problem are galactic foregrounds and continuous foregrounds. Thankfully, these are less severe at higher frequencies, and we are looking now at optical lines in order to probe the multi-electronvolt axions. So this could be H alpha and Lyman alpha lines, and therefore continuum foregrounds are not such a problem. The main problem, though, are line interlopers. These are other spectral lines that are emitted from other redshift and other cosmological volumes that received into the same observed frequency. So basically, from this sketch, we have two lines in our spectrum, but since they have different redshifts, we will be observing the contribution of the two of them. There are different ways to deal with this. Basically, one is based on masking, either blinded or targeted. And also, I prefer, though, however, since we know the lines that could contaminate sizably our maps, we could directly model the effects of the known interlopers and account for those in the likelihood analysis. And this is because these lines have still astrophysical and cosmological information. So if we keep them in our maps and keep them in our analysis, that's more information that we have. The good thing, though, is that these are only done for the known interlopers, but there could be some exotic relative decays, for example, from the axion-like particles. And I also have studied decays from neutrinos that could be detected and in the map could be as a line interloper, probably from a totally different cosmological volume that we were not taking into account. This was first pointed out by Craig Sarvinowski and Kamionkowski in 2018, not 2022, sorry. And I, again, systematized and developed strategies to deal with this, basically to treating them as interloper. So basically what I did was using the same modeling that was used to account for the astrophysical interlopers, but for the contribution from exotic decays. And in the power spectrum, basically this is seen as an exanisotropy. And this is because we observe the sky in angular coordinates and redshifts, and we need to transform this into physical distances in order to compute the three-dimensional power spectrum. And if we have a confusion in the redshift that we are interpreting our measurement in, that could introduce an exanisotropy in our maps. This in a similar way than for the Alcock-Paczynski effect in the BAO measurements. And basically, this could create and also, as I was saying, an anisotropy. So therefore, we can look for this in the high multiples of the power spectrum. Here I'm showing the monopole, the quadrupole, and the hexadecapole of the power spectrum. In pink is the contribution from the CO intensity mapping. And in the scale of blue, with the color bar, are the contributions of the CO plus the contributions from the dark matter decay. And as you can see, here we see a boost that could be somewhat degenerate with the uncertainties in the astrophysics of the CO, but the shape changes a lot in the higher order multiples. For the BID, it's slightly easier for the modeling because we only need to account for the two contributions of the two sources. And since the BID is a PDF, the PDF of the sum of the contributions is the convolution of the two. So basically, we took the PDF of the normalized densities from simulations. And since the contributions from axion-like particles traces the fluctuations in the dark matter distribution, we can obtain directly from there the contributions here for the PDF of the intensity of the of the axion-like particles. So here would be the PDF for the CO, and here in different colors would be the contributions from CO and dark matter as for different masses. Now here there is the no noise contribution is included, so basically this could be very erased, and we would stay only with the tail of the distribution in a proper map. But however, this still gives us a lot of information, and this is why we end up with this very good forecast, both from the power spectrum and the BID. These are not combined yet, because at the time I did this this work, we still did not have the model for the covariance between the two probes. So let me leave with the conclusions. I hope that I haven't gone over time. As I started, the main motivation for this work is that the cosmic optical excess for sigma significance could be explained by the case of the multi-electronvolt like particles. And one of the ways to prove this range is using the attenuation from gamma ray. We find that the measurements for the optical depth requires more extragalactic background light that is observed or inferred from standard astrophysical sources. And this can be explained, this excess, with a 14-30% increase in the contribution from galaxies at below redshift. It could also be explained with axion dark matter decays, but with lower significance. And since I've explained before, it seems that this is a bad fit. So I wouldn't believe this as a potential explanation for that residual optical depth, which what we need to be left with is the strongest constraints that we find at 3 sigma in the range between 8 and 25 electron volts, and also the nice future that we have for this range. First, looking only at the attenuation from gamma rays, the measurements in the gamma ray range are only going to improve because current observatories are going to keep observing and improving their measurements from the known blazars, but also there are very nice future gamma ray experiments, such as at least, for example, in the Cherenkov telescope area CTA, that is going to start in the coming years. And also, I expect very high improvements of the extragalactic background light determinations, which I believe right now is the main limit and the main bottleneck for this kind of analysis. And I expect these improvements from experiments like SPHERIS of the James Webb Satellite Telescope. Finally, there is a huge improvement in sensitivity in the prospects from line intensity mapping, so I'm also very excited about that. And I forgot to say something, and I can say it with, let me go back to it here, that you can read this plot as you want. There is a tiny overlap there with the contribution that could be explained from the in order to explain the cosmic optical background, but still some part of the contributions with the actions, not maybe to explain all, but to explain part, could be there. So I apologize for all the issues with the slides and the figures and everything, but thank you very much. And if you have any question, feel free to ask. We didn't, because in the end, the two models with it's true they don't have the same number of parameters, but it's they are the parameter space of them is very simple. We could have done it, especially because as you can see here, at least for this case, the posterior is anything but Gaussian. But in the end, what we did was a 2D likelihood of the exploration of this parameter space and perform a delta chi-square in order to set this posterior. So we would have done it, but we've done this without running Monte Carlo because we didn't need for this parameter space. So I don't expect a lot of difference between the results that we get, possibly in the interpretation, but qualitatively, I expect the same result. Yeah. So okay. So I said this, I included this one here for basically give some kinds of context, but this part of the parameter space is ruled out by globular clusters, by the stellar cooling of globular clusters. So this part of our posterior could be ruled out by other explorations. And I don't remember right now. So cast starts here. I think that this tiny range here is available. And right now over here, there is some space, but future haloscopes, I think, and experimental searches are going to improve this range. Yeah. I mean, I'm no expert in stellar physics, but I think that the constraints from the stellar cooling are pretty robust. I don't know what other people in the in the audience believe, but they are. If I don't remember wrong, this result here, that the one that I'm plotting here, is pretty old and haven't been disputed. So this started basically. This wasn't designed for this at all, but Senkov and collaborators go use some of the archival data they had, and I think that there are some here. So it's like this upper limit is from that archival data because they were pointing everywhere. This gray data is from last year already from using archival data, but already outside of the solar system. And finally, this one is after showing that, how promising this was, targeted observations of dark patches on the sky. So these are small fields, different fields looking at different dark sides. And in this case, these dark patches is in order to basically not pointing at the Milky Way and remove contributions from bright stars from close by galaxies. Yeah. Yeah, but this one, the one that of this year, the one that has the 4 sigma, it's not with archival data. This is already targeting in purpose those dark skies. And I think that this one is one or maybe a couple, but they are performing more observations. So I expect it to improve. Yeah, it's impressive. Sorry, it's the same. I had to run over there, but basically what we have this is we perform this kind of modeling for the line interlopers for known astrophysical lines. But if we have a decay from dark matter or neutrinos, that will give us a spectral line that is not around the catalog of known lines. And basically, we perform the same analysis for interlopers, but basically marginalizing or like looking for masses or frequencies of this line that are not within the catalog of spectral lines that could be interlopers. Yeah. So we have this kind of line here in a real analysis where you have the contribution from interlopers and you have like maybe there are like here a spike of worsening the constraint because in that case you have another line that you could be confusing with. So this is from spherics and head-decks. I think that head-decks is only Lyman alpha and spherics is Lyman alpha and H alpha. Here in this case, we don't consider the interlopers. We consider the targeted line, the line that we are targeting, and the interloper from the dark matter, because this was a preliminary study of the sensitivity for this probe. For Lyman alpha, the interloper, and for H alpha, I think the main interlopers could be oxygen lines and H beta, I think. Yeah. But as far as I know, and I've heard, at least head-decks is returning results that are very exciting. I don't know honestly, but this would be like much higher frequencies in order to deal with the CMB, right? Because these are like in the electron volt, so these are optical photons. Yeah, I for example checked for the gamma ray background. Sorry, for the gamma ray attenuation, I checked whether the CMB photons would contribute to the attenuation, but they are too low energy to interact at all with it. You will need extreme high energy background that are not even detected by the Cherenkov telescopes in order to be able to interact with the CMB photons. So yeah, I did this analysis for the intensity mapping with much lower frequencies because let me see where is this here. Because I was focusing for that plot for the context of the talk in spherics and head-decks, but there are experiments targeting a whole plethora of lines in a very big range in frequencies. This going from like the radio to the optical. So we would be able to probe in general around like, I don't know, 8, 9 orders of magnitude for the mass of the electron volts. But the rest of the probes, the rest of the experiments couldn't be competitive with other actions searches, for example, from haloscopes in the future. I think that they are competitive with CAST, but not with YAXO, or I don't remember if even with CAST they are competitive. It's nice though, because for in the submillimeter, you would be able to set constraints in the neutrino decays. And in that case, there are also constraints from the spectral distortions. But in this case, for the analysis that we did, this would be more powerful, especially with Atlas, which could be a potential basically replica of SDSS, but in the infrared. And we are trying to include an intensity mapping survey in it. I think you had a question, Bradley? Yeah. So the case for the gamma rays is also an excess, basically in the optical and in the infrared, because what we see is an excess in the attenuation. So we see too low of gamma rays with what we would expect from astrophysical searches. So basically, we are probing the EBL kind of in the same range. For the gamma rays, is a bit more extended. We can change the luminosity function in the faint end because that's the one that we are not observing, and it's just an extrapolation of what we have. A priori, you have infinite range there, but some of the values, of course, don't make sense. I haven't tried to fix with variation of that, the two at the same time, because as I was saying, with one, you basically probe all the integrated contribution at receive 0. With the one, you have more information. So I don't know if there is a space to tweak everything properly for both. Thank you very much. Yeah. Yeah, I'm in one of the offices upstairs. I don't know which. Okay.